Okay. So it is recording is ongoing. Yeah. So this one was better. ये मैंने सुबह भी ट्राई किया था. ये गेम बार वाला हटा दूंगा मैं फीचर. Okay. So yes. So I was telling you about, so we have this equation, and okay, so this is a green and blue is the imaginary and this part that we are talking about, and this constancy of this probability that is shown by the blue color, that is a particle. If it is ball, presence of the ball all over the place, it is has the same probability, so that is indicated over here. In the previous classes also I discussed this point, that if you have a simple n to the power e to the power ikx plus like this, something like that, so this is the equation kind of thing that you will emerge. So that is a case of I think. Now let's try to understand these constants that a and b are there. These are to represent they represent how the state of the motion, uh, how that equation has been arrived at, what are the components that overall define that motion. So that is, so just in case, if you remember, you had the earlier example of cos kx was constituted by half e to the power I kx, the previous one, in the previous examples that we have discussed. One of the case was that. So it has two components, e to the power ikx and e to the power minus ikx, and a and b were equal, having half value, same value of half. So that was the equal contribution of the two wave function, and that constitutes the motion, state of the motion. So that was the previous one of the examples that we discussed in the previous classes. Okay, so that is what we mean by how that state of motion has been prepared. That is what we mean. So more precisely, if we want to talk about the first one, that if it is shot, if throw the ball along the positive x direction, its linear momentum is plus kh cross, and the wave function will be proportional to this e to the power ikx, the first term that you are having in your equation. In this case, so if the ball is continuously moving in plus x direction, so that is a movement, net movement. So अगर आप ट्रांसलेशन मोशन की बात कर रहे हैं, बॉल एक तरफ तो एक कोई नेट मोशन होना चाहिए. अगर नेट मोशन होता हुआ कि पॉइंट ए से पॉइंट बी की तरफ गया है, यहाँ से वहाँ ट्रेवल किया है along x, so there should be a net movement, and that will be described by, say, if it is the movement is along the x plus positive x direction, so e to the power ikx is the function that you need to describe the motion of a particle moving along plus x direction. So in this case, because it is moving only in one direction, plus x direction, in this case b will be 0, second component, because there is no component of if it is not going in the minus x direction, the capital B term should be 0, and a will be treated as the normalization factor here. And so in the second case, we can imagine that the ball has been, you throw the ball in the opposite direction. एक बार प्लस एक्स की तरफ आपने फेंका, तो उसके लिए अगर आपको इक्वेशन लिखना पड़ा, तो आपने e टू द पावर आई के एक्स होगा, तभी वो आप एक ट्रू मोशन डिस्क्राइब कर पाएंगे. दूसरी तरफ आप देखेंगे कि in the same manner you think that if you can think of throwing the ball in the opposite direction, minus x direction में throw किया, so if you throw the ball in minus x direction, then the linear momentum will be minus kh cross, and the wave function will be e to proportional to e to the power minus ikx. So in this case, in the second case, if it is moving in the minus x direction, there should be no component from the others. So to represent that, a must become 0, the constant a. So there is this wave function doesn't, in that case the first term will not contribute and you will have in original, so A will be 0, B will become the normalization factor. So in this sense, so what you are seeing here as a general feature, to describe a real motion, पॉजिटिव एक्स डायरेक्शन की तरफ मूव करता हुआ, गाड़ी एक डायरेक्शन में जा रही है या बॉल एक मूव कर रहा है जैसे, ऐसा सोचिए. सो इफ अ पार्टिकल इज मूविंग इन अ नेट, if there is a net motion from point A to point B along positive x direction or along the negative x direction, each one of them is described by one type of function, e to the power I kx or e to the power minus a kx. So in order to describe a net motion in quantum mechanics, a true motion, a real motion, there must be an imaginary term. Without that imaginary term, you cannot think of a real motion being described. आप किसी भी रियल मोशन को क्वांटम मैकेनिक्स में डिस्क्राइब करने के लिए आपको आई के एक्स टर्म आएगा ही आएगा और रहेगा, तभी आप रियल मोशन उसको डिस्क्राइब कर सकते हैं. Otherwise, it is just not possible. So the example, for example, if you have wave function this and this, uh, so so a particle with net motion is described by a complex wave function. There must be both components, real and imaginary components. So complex wave function होगा ही होगा. मतलब I का टर्म, इमेजिनरी I वाला जो है ना टर्म, वो आएगा ही रहना चाहिए, तभी आप नेट मोशन को डिस्क्राइब कर सकते हैं. Okay, so that example you can correlate with when you had previous example of if psi is equal to cos kx, and in that case a and b were equal half, तो इसका मतलब ये भी होता है कि overall there is no movement, the particle has no net movement in that case. So and it was a real function, so cos kx is a representing, it is a real function, and the real function is not uh, uh, when we write a real function, it is not corresponding to a net motion of the particle. इसमें आधा आधा कंपोनेंट दोनों तरफ का है, पॉजिटिव एक्स डायरेक्शन का भी है, माइनस एक्स डायरेक्शन, बोथ कंट्रीब्यूट इक्वली, सो नथिंग हैपेंस, देयर इज नो नेट मूवमेंट ऑफ द पार्टिकल. ओके, so that corresponds to so zero, so there is no net movement, so you can say zero net motion. So ये कट क्यों रहा है इधर स्लाइड? ओके, सेटिंग्स का प्रॉब्लम है. Okay, so zero net motion, that means, and so we have, so to describe a real motion, a net movement of the particle, there must be an imaginary term coming in the wave function. So the wave function, that means the wave function itself must be a complex wave function. ओके, कम्प्लेक्स मतलब एक कॉम्प्लेक्स वेव फंक्शन ही एक नेट मोशन को डिस्क्राइब कर सकता है, एक रियल वेव फंक्शन नहीं कर सकता. एक देयर इज नो नेट मूवमेंट व्हेन यू राइट अ रियल फंक्शन, इफ यू एनालाइज इट you get nothing out of it for kind of thing. So so if the particle is having e to the power I kx, pure this one or this one, its probability is given by psi square, and that will be uniform. Uh, Pure momentum states of this, uh, and according to the Born interpretation, what you have learned, you cannot say anything about the location of the particle. If probability density is everywhere the same, you cannot talk about this thing. So that is all right, because we have learned already that if we, because we know the momentum with certainty, कि अगर हमने इस तरफ प्लस एक्स डायरेक्शन में बॉल को उछाला है, if we have thrown the ball in the along the positive x direction, we know for certainty that it has plus kh crosses the momentum, 100% sure. So we are totally uncertain about the location of the particle. So that is in agreement with the uncertainty principle that we have learned. So and agreement with the complementarity of the observables. So that is there uh, because the operators do not commute. So similarly we have okay, so this and so let's talk about this so this so we have seen that so free motion of a particle we have discussed, and in this motion any value of k is acceptable. K is continuously changing if you and so this is we have also learned that energy is not quantized in this case. We can have a is equal to 0 or b is equal to 0 to describe a net motion of the particle either in plus x direction or in minus x direction. Okay, so these are the so this is the free motion that we were talking about. No quantization emerges in this case because any value of k will be acceptable. There is no such and so the energy will also be changing continuously. Okay, now we will discuss a case where the particle is trapped between like you keep in a box and it is cannot come out of the box, something like this. So that is called typically particle in a box model. Very famous thing. You must have heard about it in your bachelor's classes. BSc में भी सुना होगा. And this is one of the most fundamental concept of quantum mechanics, and it is also an application of the Schrodinger equation that we are going to discuss. So in this, it is assumed that suppose you have a two high energy walls. Uh, so these are high energy walls at the walls, okay, at the two ends. Walls, and the particle is here is supposed to be inside the box, and the particle can only move it can have what we say v for the particle is inside, and this particle can have a net motion sorry it will have v will be potential energy will be 0 inside and v will be infinite at the walls. So any system will try to minimize its energy, and the particle will be moving with a kinetic energy certain kinetic energy will be there associated with the particle, whereas the potential energy v will be 0. So this concept we will be discussing in detail. So particle can move from 0 to L. So this is along the only in one dimensional frame that we are discussing. So it is only in x direction 0. The coordinates are discussed in this frame are 0, and it is the length of the box up to capital L, shown by as capital L. So particle can move from one end to the other, but it cannot penetrate. It cannot penetrate, go across the wall, because the energy is going up to infinity. So particle will, as soon as it touches the wall, it will come back. It will start its reverse movement. It will, but so it will be keep like a ball bouncing between two walls. ऐसी situation होगी. So particle in a box so we can consider to be having a mass m, particle of mass m, and it is confined between two walls. Confined मतलब कर देना मतलब उसको restrict कर रहे हैं आप, उसको बाहर नहीं जाने दे रहे हैं. So that is confinement. If you are locked up in a room, you are confined. You are so that is uh, So you're putting restriction on the motion not to come out of some place, so that is confinement. Okay, and the confinement is such with a location x is equal to 0 and x is equal to L. These are the coordinates, so representing the uh, uh, motion can take place from 0 to L, and it cannot go beyond L or less than 0. That side it has to, because the potential energy rises very high at that point. So this is there is abrupt rise to infinity. So that abrupt rise prevents to infinity, prevents the ball to penetrate, go across the wall. So this is something that is of quite an interest. Even nowadays फिर से लोग इसको समझने की कोशिश कर रहे हैं. So there is a resurgence of interest among scientists also. क्यों? सिर्फ इसके लिए नहीं कि हमें सिर्फ बहुत सारी चीजें हैं, क्यों होता है, कैसे होता है, वो समझना है, वो तो है ही. उसके अलावा there are many things that you can make out. If you understand this well, you can make devices, you can make things which will be wonderful. I mean, that will improve the quality of life. So, with that intent in mind, we try to understand this translational motion, that is, and one of the classic example, particle in a box model. So this concept has been realized because this quantum mechanics, the particle in a box model, can be applied in semiconductors, that where the crystal can act as a box and the charge carriers such as electron and holes act as particles moving in the crystal. So that is particle in a box kind of model. And then the surface is always have a high energy, so they resemble the two walls. So a real situation, uh, physical situation can be created, and that can be utilized, that will have properties which you can never have imagined. So such things have happened, and that's why we see that we are having a renewed interest in this particle in a box model. So what you see here is you must have heard about the Samsung QLED TV. It was recently launched a few years back. So the what do you know what this Q stands for? Q stands for quantum dot. Q stands for quantum dot. Quantum dot. So quantum dots are a special type of semiconductor energy. So this is a real application of particle in a box model. Something, and the device, so they, the variety, the beautiful colors, the multiple shades of color that they are able to regenerate. So this is a classical application of quantum dots, quantum wires. These are different terminology given to nanomaterials and how they are prepared and what is the length scale and that thing, if you can describe. So we are not going into the details, but to just to tell you that this is the level that we have reached in this context when we are talking about particle in a box model. So a very good understanding of a particle in a box model can lead to, these are the things that comes in the life of a common man, affects the life of a common person, layman. So this is the restriction, जो मैंने कहा ना, restricted movement. आप confine कर दो 3 dimensional space में, electrons or holes are treated as particle, the crystal becomes the box, and so you will create a real life situation, uh, 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 a true physical example of which can be shown in laboratory. So this is similar things we have been also doing in our labs. You can undergraduate students, postgraduates. So people have synthesized this in our labs. So this you can see that variety of colors. This red, green, blue. ये पता नहीं ये कट क्यों रहा है मुझे. अच्छा फुल फुल स्क्रीन नहीं हो पा रहा है. Somehow it's not going full screen. सो इसलिए पिक्चर थोड़ा सा कट जा रहा है, ये मुझे दिखा नहीं पा रहा हूँ ठीक से। So yes, so this is what I was talking about, why the interest has been, and these are the things that so this is the size dependent colors that you see. So this was something unthinkable before. Chemically it is same cadmium telluride, but because of the but they are emitting different colors. It kept in UV light. This is the image taken in UV light. You see different colors are being emitted. Luminescence कहते हैं, fluorescence जिसको कहते हैं वो आ रहा है, green से red orange सब, yellow orange. So this is another application of this particle in a box model. Good understanding of quantum mechanics can lead to such things. And a very small change in size, 0.2 nanometer change in size is giving us the change in colors. So this is something that we have done. This similar type of quantum dots have been used in QLED TVs, and the bulbs are also being designed on that line. So display systems and LED bulbs that you can talk of. So they are good because they consume a little amount of electricity and produce wonderful image quality, long lasting. So all because of the advantages the people are preferring. So it is happening because of, so that is one set of application. If you understand particle in a box, then you can design those things. It also forms a basis when you have uh, like butadiene. If you have a long chain molecule, electrons are delocalized throughout the chain. So that so if you can visualize that big molecular orbital which is in one dimension, उसमें जो इलेक्ट्रॉन होगा to and fro, it cannot go out of the that orbital. So it is like a box trapped in an electron trapped in a box, something like that. You can imagine if it is all in phase association of the, so like this. So this is again something that we can apply over here. We will see later on, we will do these things, we will apply these things. So some numericals will be solving later on, taking example after understanding of having developed understanding for particle in a box. We will further apply this to understand the like in carotene, uh, there is also a long conjugated chain, hydrocarbon chain. So there also you apply these principles, uh, and that helps you why you are getting that orange color or something. So all those things required. So one dimensional particle in a box, this is the model which can be used to understand movement of electron inside a long chain molecule like this. And the one that semiconductors I have already talked about. So that it, and that understanding leads to फिर आप उससे आप बहुत सारी चीज़ें कर सकते हैं, something that will be useful. And so it is also used in statistical thermodynamics, which will be in the next semester. We will be doing it, taking contribution to translation motion of molecules. So this is how we visualize these things. So we visualize this motion. Okay, so when you have this thing, you can think of, yeah, so particle trapped in a box. So this is at the, so this is what we are talking about here. The energy is, potential energy is infinity, potential energy is infinity over here. So particle will just move to and fro, x is equal to 0 and L. So the same thing, this is a particle viewed from one point. This moving particle, when you realize its wave-like features, wave-like nature, then it can have either this one or this one or this one. So one loop, two loops, or three loops. So all of this is possible. We will see how it comes. We have not yet gone through. So this is the just a pictorial view, just to make you interested in the thing, that why we are doing it, how it is going to help us. So we started with this equation, the simplest form of Schrodinger equation, the kinetic energy operator, potential energy operator, and then E psi. These are the walls with infinity potential energy rising to infinity. Potential energy is zero inside the box, and so because the potential energy V is equal to zero, this term is gone. This reduces to zero, and you are left with only this term, kinetic energy term. To describe the energy, you only need this differential equation. Uh, so the Schrodinger equation of a for free particle for particle when it is between the walls, and when it was a free particle, free as compared to a free particle, the nature of equation is appearing to be same. So the general solutions will be of same type. The equation that we can write, first term, second term, and then you can try to expand this. E to the power I kx is cos kx plus I sin kx, and so you can write in the same way e to the power minus I kx, that can be written as, just change the sign over here and rearrange this equation. If you rearrange this equation, you are getting these terms, a plus b cos kx. So collect all the terms, that cos kx terms, and a minus b I sin kx. So you can label it as d, and this as c. So something like this you can write, then c sin kx. So this whole term becomes c. So you can write c sin kx and d cos kx. This is as for the motion between 0 and L. So length of the, so starting from 0 is, if these are the coordinates. So this is the simplified version of the wave function, keeping in view. And so the energy would be, if this is the equation, then kh cross is the momentum, and so we have the energy is simply k square h cross square by 2m. So energy is given by this k square h cross 2m, and when the particle touches the wall, it rises to infinity. So it is never going to cross through that. So the amplitude must become zero. The wave function must become zero at the walls. So amplitude of the wave is zero at the walls. Okay, it has to be there. For x is less than 0 or x is greater than 0, L, psi k, the amplitude will be 0, and there's, so psi k, the value of wave function will be 0, greater than that point. So we, as we can apply the postulates that we have learned earlier. So the requirement is that wave function must be continuous. The slope of the wave function, that also must be continuous. So we can put this, apply this, that the equation whatever we write must satisfy these two conditions, and these two conditions, we also call it boundary conditions, because it is at the two boundaries of the box. They represent the two boundaries, and at the two boundaries you have potential energy rising to infinity. And so you put it like this, so psi k becomes 0 when, so within the bracket it is the value of x that we have put in. Okay, it is the value of x that is 0, it is the value of x which is equal to L. So rather I should put this arrow like this. So this, it is the value of x that we have indicated, and for x is equal to 0, the function goes to 0. For x going to L, capital L, the function goes to 0. So these are the things that we hmm. so so when we try to understand, so which means, so when you want to make it out, the boundary, the waves must have to be continuous, and the amplitude of the wave must become 0 at the wave. So if you're looking at the wave profiles, you can simply generate a few things. सिर्फ पिक्चर्स से ही आपको बहुत कुछ समझ में आ जाएगा, थोड़ा ध्यान से देखिएगा. So a general wave like profile has been drawn, two types of profile, and we can easily find which one is acceptable, which one is not acceptable. So see this red one, it is having a finite value, finite value at when you have capital L here, this is 0, x is 0, x is equal to capital L. So this is a finite, so obviously, so this is not satisfying the basic postulates that we have framed for the quantum mechanics, and so this cannot be accepted. But look at the green one, it is 0 here, it is also 0 here, becoming 0 at the wall. So at the two ends, when x is 0 and when it is x is equal to capital L, in both cases, so this is satisfying the conditions. If it satisfies the condition, then you see, if you are making these loops, so look at this green one, 1 2, so 1 2, so it has to be a integral multiple of half wavelength. So this, it should turn out that the capital L must be n lambda by 2. So you are fitting like in this particular form, you can see when it is lambda by 2, only then at the two ends you are having 0 value. देखिए 0 तभी होगा जब lambda by 2, ये एक लेंथ है, this is, what is this, 1 lambda by 2, this is another lambda by 2, this is third lambda by 2, then another lambda by 2, then another lambda by 2, and in this way finally this last lambda by 2. So half wave, it has to be an integer multiple of half wave, half of the wave, this is lambda. So if it is lambda by 2, then a multiple of lambda by 2 satisfies these conditions. L is n lambda by 2, then it is happy. So if you remember in the first few classes in offline mode, I have told you about standing waves. When a string is tied at both ends, look at this, it is similar situation. There also it was lambda by 2, multiple of lambda by 2 was coming. It is similar thing over here as well. Okay. So these are the things that you can have, integral number of half waves. Okay, so you cannot have any other things because any other values, if you have other than this case, they will not be, it won't become 0. The waves amplitude should become 0 at both the walls. So no matter you are, so you are, so see, gradually you are increasing the curvature, the energy is rising. First one, n is equal to 1, lowest least curvature, then curvature is increasing. See the bends, sharp bendings, n is equal to 5, 6. So apply those principles that you have already learned. Looking at the pictures, you can apply this principle and see. So energy rising, curvature is increasing. You can simply see and see. Okay. So you have to fit in the box. So these waves need to be fitted in the box, and they can fit only when they are integral multiple of half wavelengths. One bulge, one bulge, two bulge, so 3, 4, 5, so n is equal to 5, so there are 5 bulges like this. So this is the bulge, means something coming out of area. So this is one bulge, two bulge like this. So this sum of these should be equal to the L, capital L. So that's what we have to think. So we consider each wave functions to be a de Broglie wave, and this wave must fit the container. So to fit the container, they must be integer multiple of half wavelengths. So if you put these conditions, then you can arrive at all these features. So this is the same thing being represented through. So this is n is equal to 1, n is equal to 2, 3, 4, and so on. Okay, so it is the lambda by 2, 1 lambda by 2, 2 lambda by 2. So you have to fit it like this. So this is lambda by 2 and another lambda by 2. So 2 lambda by 2, and in this case it is lambda by 2, another lambda by 2, and third lambda by 2. So you can see 3 lambda by 2, very easy, equals to the length of the box. So a simple thing that we can see, that to fit, if we try to fit the wave profiles within the box, they must be half multiple of half waves, integer multiple of half waves, and that should be equal to the length of the box, capital L, where n can be 1, 2, 3, and therefore lambda is 2L by n. So this takes us to this point, that 2L by n, and this L, so you can see that the wavelength cannot vary in arbitrary manner. It cannot have any arbitrary value. It is not continuous. So lambda can change only in multiples of 2L by n. Okay, where n is 1, 2, 3. So that means the energy will, so each of the lambda is associated with certain energy. That means energy will also change in a certain fashion. It is not continuous. Energy is not continuous in this case. Okay, so here you can apply this. So you have h by, so what is momentum? H by lambda. So lambda, we have already 2L by n. Substitute it. So substitute this value of lambda over here, you get n h by 2L. So momentum has been defined. So now you can, if momentum is defined, you can define the energy, p square by 2m. So that also you can arrive at, and you can get, so applying this, you can get to this point. So put the value of p, momentum, and you are there, n square h square by 8 ml square. So see, this was the easiest way to derive the expression of energy for particle in a box. We simply try to see which is the smallest, starting from lowest possible uh, first case, that the two ends must be 0. So if we make a wave profile, it is a half wave, then you can make fit it, 2 half waves can fit, 3 half waves, 4 half waves. So as long as it is an integer multiple of the half waves, it is perfectly fitting the container, and that is valid. So that particular profile can be described by a certain wave function, and that should be acceptable as a solution to the Schrodinger equation that we will write. And so if we are fitting this, we can easily find a pattern emerging in that lambda n lambda by 2 is equal to L, and so lambda is 2L by n. Put it over here, momentum nh by 2L. Then again, so if momentum is known as nh by 2L, you can find the energy, and that's it. You are there. You have found the energy for the particle in a one-dimensional box. So there is second approach as well to derive the expression of energy, but this is a more formal, more mathematical kind of approach. Uh, First one is also correct. Nobody can say that is wrong. You have a sound logical argument to reach there. Okay. So a second approach can also be taken, and so few more minutes. Yeah, it will be slightly longer. It's the second approach. So this one is like you apply the boundary conditions at x is equal to 0, the value of wave function must become 0. So you have reached, this was a wave function that we have written, c sine kx plus d cos kx as the general one. So when x is 0, just realize a few things. When x is 0, what will happen? Sine kx, substitute the value of 0, so this term goes to 0, whole thing goes to 0. Sine 0 is 0, so only cos kx remains. So cos 0, if you put the x is equal to 0, cos 0 will become 1. Okay, so put this, so that means psi k is equal to d. Okay, so that means d is 0, because psi k has to be 0, x is 0. So this is the boundary condition, it touches the boundary, and the psi must be 0. इसका मतलब तो d 0 हो गया, d should be 0. So it follows the wave function must be of the form, इसका मतलब ये हुआ कि अगर d 0 हो गया, so then c is certain, so the equation that will remain is c sine kx. And so this is the first, we applied the first boundary conditions, and we have reached that d is 0, and so we are left with only one part, c sine kx is there. Okay, c must be something, so apply, and so now we apply the second boundary condition when the length is capital L. दूसरे वॉल पे चले गए, पहले वाले वॉल पे लेफ्ट साइड वाला वॉल, फिर राइट हैंड साइड में जो वॉल था उस पे जा रहे हैं, तो उस बाउंड्री पे पहुंच के इट इज द लेंथ x का वैल्यू L है, so your x is L and it must be 0, the whole wave function should be 0. So what is your wave function? So when you substitute the value of x is L, capital L, so we are substituting this x value, so it becomes KL. So c sine KL must be equal to 0. Now if we take c is equal to 0, now there's two things, either we can make this term 0 or this one is, with any one of them we have to make it 0. So if you make c is equal to 0, if we make that, that would means that for all values of x, psi will be 0. Okay, so that is not correct way, obviously, तब तो पार्टिकल का कुछ एग्जिस्टेंस ही नहीं होगा. अगर psi वेव फंक्शन ही 0 हो गया हर x, for every value of x, the particle can never be found anywhere. So it is against the postulate 2, particle must be within the box. Okay, the second alternative is that you set the sign KL to be 0. So KL must be chosen in such a way that sin KL becomes 0. So this condition, how we can is possible if KL is equal to n pi. If KL, the length, the wave vector k, that is 2 pi by lambda L capital, this term should be equal to n pi, then you put in sine n pi, then that should be, when n is 1, you put the value, sine will be coming out like that, it will become 0. So the value n is equal to 0 is ruled out, because then again it will mean that you have k is 0. So n 0 कभी नहीं हो सकता, k is equal to 0 and psi kx is 0 everywhere. So n is equal to 0 is not possible. The k is the wave vector and 2 pi by lambda cannot be 0. So k is what? It is the wave vector. बार बार मैं कह रहा हूँ, which is equal to 2 pi by lambda. So this cannot be 0, other it has no meaning if you put it like that. So n 0 acceptable नहीं है. We have to start with n is equal to 1, lowest possible value which is acceptable. Okay, and then negative values of n will have no meaning, because it is the sine of sine kl, because sine minus x is minus sine x and do not result in new set of solutions, so you are repeating the same thing. So the solution is something, so you substitute this, so kl is n pi, which implies that k, so you substitute this thing, n pi by l, substitute k is equal to n pi by l. So this form, and substitute, we have substituted over here in place of k, so n pi by l into x. So this is the solution. Okay, so here we have now labeled, so now we are starting to label it as n, the quantum numbers n 1 2 3 like this. So this is something that you see. So we have get rid of k को हमने replace कर दिया है पूरा का पूरा, and we have a in terms of n pi by l, and so we are also writing the psi. When we are writing psi, we are, instead of labeling it with it k, so note this point, here it was k, now the subscript that we are putting is n, because we have replaced the k part with n, and so indexing is done with n now, and this is the equation. Energy is this, k square h cross square by 2m, kl are related by n pi. So the energy of particle can be written, so kl is n pi, so substitute the value of k from this n pi by l, and you are here, you have derived the value of energy. Another way to find the energy, and c is, we have not yet determined the constant c, so this is a task yet remaining, so we have to follow a few things. The presence of boundary conditions and the constraints on the wave functions. Okay, so we have already discussed this, that only certain wave functions are acceptable. We have seen that either one loop, two loop, so half waves profiles are acceptable. So these are, now we are labeling them with the dimensionless thing. Okay, so this thing, so the general solution that we arrive at is that, so this is the two things we have already, so we have to satisfy boundary conditions in conjunction with the general requirement of postulates 2 and 3. And this is what we find, that only certain values of wave function are acceptable, and the observables, that is the energy, momentum, they have discrete values. That means they are not continuous. This is the emergence of quantization that we are seeing here. So energy has been quantized when an a particle is trapped in a box, such that the condition that we visualize, that energy rises to infinity at the two ends of the wall, at the two walls. And there are other things that also we will see it is quantized. Gradually we will find that. So what we have to determine C. So we have not yet normalized the wave function. That is a task that is remaining. And so the wave function can only be found, the particle can be found only between 0 to L. So outside that, wave function is going to be 0. Outside the box, wave function will be 0. So if you try to find the probability from 0 to L, it should be equal to 1. Probability of finding the particle within the box from 0 to L should be equal to 1. So you have this function C sine n pi by L. So square it and write the function. So you do it. So when you do this, you can square it like this and then write this part. So now you can evaluate it. So integration करो, integration हो सकता है, और then you integrate it and find. So you find that on integration you will get this value, c square L by 2. And so finally you are getting the value of c, which is under root 2 by L. ठीक है? Now your wave function is complete. You have evaluated the c has been evaluated. You know now what the value of c is. So put this value over there. You have written a complete wave function, which is, so this is the complete final expression of the wave function. Okay, psi n, the function of x, is under root 2 L, like this, n pi L x. So, and rest of the things we can continue tomorrow. ठीक है?